Hello everybody, welcome into another lesson. So you're probably wondering, what the heck is this an abomination of a graph? This is what we call crazy graphs. These are usually just man-made by your professors. This isn't even a particular function. The idea of this type of graph, or crazy graphs in general, is for you to be able to find points of discontinuity, identify what type of discontinuity they are, find the value of that function at that discontinuity, and determine, is that function continuous from the left, right, or neither at that point. And of course, take the limits of those functions at that point. Well, now since we've talked about all four types of discontinuities, the removable discontinuity, the jump discontinuity, the infinite discontinuity, and the endpoint discontinuity, this is the last lesson on discontinuities where we're combining all four of them into one graph, and now you have to identify which one it is. So let's look at this graph here of this hot mess. Let me make sure. Okay, good, I'm on. Alright. So let's look here. If we look at x equals -4, we see it's the farthest left this graph goes is at x equals -4. That's actually a discontinuity. That's of the endpoint type. We have an endpoint discontinuity at x equals -4. So, endpoint discontinuity is going to be located at x equals -4. Now, what we have to assess here are a couple of things. One, what's the value of the function at -4? In other words, what's f of -4? Does it exist? So let's determine about f of -4. If we look here, we actually do have a solid dot at f of -4, which tells us the function is actually defined there, and that would give us a y value of 3. So f of -4 actually equals 3. Now, the next thing we want to determine is the left-handed, right-handed, and general limits of this point of discontinuity. So let's take the limit as x approaches -4 from the left of this particular function. Well, if we approach -4 from the left, that means x has to be less than -4, and this function's not defined for such values. So right away we have a left-handed limit that does not exist, which means the general limit for sure won't exist, but we still need to answer the question of what's the right-handed limit. So what's the limit as x approaches -4 from the right of this function? If we trace along this graph to x equals -4 from the right, we get to that y value of +3. So the right-handed limit's +3, but the left-handed limit doesn't exist. So therefore, the general limit as x approaches -4 of this function actually does not exist. Now, the next question is going to be, is this function continuous from the left, right, or neither? Well, it's definitely not continuous from the left because there's no values of x less than -4, but we see at x equals -4 going towards the right, it's continuous because it's actually defined at -4 and it continues right, so it's continuous from the right. So this function would be continuous from the right at the value x equals -4. So again, you have an endpoint discontinuity at x equals -4. F of -4 equals 3. And then you have the left-handed limit as x approaches -4 that does not exist. The right-handed limit at x equals -4 is 3, which means the general limit at x equals -4 does not exist, and this function is continuous from the right. So that's all to deal with x equals -4. Let's look next for other discontinuities. There are plenty more, I promise you. Well, okay, so it looks like at -2 we have another discontinuity, and if you look at it here, we have a jump discontinuity because you jump values from the left and right hand side, and even in the middle you have it where it's actually defined. So you have a jump discontinuity located at x equals -2. Now, the big question first is, what is f of -2? Is the function actually defined there? Well, if we look at the top part going left, it would look like it equals +2, but you have an open circle there at a y value of 2, so that means f of -2 can't be 2. Then if you look down below and going right, it would look like it has a value of -2, but it's also an open dot, meaning, or an open circle, meaning it's not defined there. But we have a solid dot at a y value of 1. That means f of -2 itself is going to equal +1. So we got f of -2 itself equals 1. Now, what about the left-handed limit and the right-handed limit? So the limit as x approaches -2 from the left of this particular function, if we go along the curve and trace to the left as x approaches -2, we get that y value of 2. Now, what about the right-handed limit? So if we take the limit as x approaches -2 from the right of this function, so go along your curve, trace to the right at x equals -2, you would get a y value of -2. So you got a left-handed limit of +2, a right-handed limit of -2. That means your general limit at x equals -2 doesn't exist because the left-handed limits and the right-handed limits don't match. So, therefore, the general limit at x equals -2 doesn't exist. Now, the next question is, at x equals -2, is this function continuous from the left or the right? Well, if you look at the left branch as x equals -2, notice it's undefined for that y value of 2, and if you look to the right branch as x equals -2, it's undefined at the y value of -2. So in this case, it's continuous neither left nor right. So this function is continuous neither to the left nor right in this case. So that's everything about x equals -2, that discontinuity. And if we look at this graph, it looks like we have another discontinuity at x equals 0. We have an open circle at x equals 0. So we definitely have a discontinuity there, but it's just an open circle at that one point. The rest of the curve's filled in. So this is a removable discontinuity. So we have actually a removable discontinuity at x equals 0. Now, the next question is f of 0 defined? Well, it's a removable discontinuity, so we already know that f of 0 is not defined. So f of 0 in this case does not exist. It's not defined there. Now, we can take the left-handed limit and the right-handed limit and find the general limit. So the limit as x approaches 0 from the left of this function, if we go along our curve and trace till we get to the left of 0, we get a y value of 0. So the left-handed limit is 0. Now we need to find the right-handed limit as x approaches 0 of this function. So let's take that right-handed limit. Again, trace along your curve to the right until you reach that x value of 0. You would also get a y value of 0. So in this case, since both limits match, we do have a general limit at x equals 0. The general limit as x approaches 0 of this function in this case would be 0. Now, here's where it gets tricky. This is where it can get tricky. Is this function continuous from the left, right, or neither? Removable discontinuities can really stump people. Do yourself a favor from the second. Pretend that this left branch don't exist, because after all, this is a removable discontinuity. You can treat this as an endpoint at x equals 0. You would only have the right branch. You would say it's not continuous from the left, and then we can also apply this rule to the right hand side. So pretend you only have the left branch and the right branch doesn't exist for just a minute, because this is a removable discontinuity. At that point, x equals 0, the value itself doesn't exist. So for a removable discontinuity, it's also continuous neither left nor right. So for removable discontinuities, it's actually continuous neither to the left nor right. And that's true for all removable discontinuities. So there's everything about x equals 0. If we look at our graph here, it looks like our next discontinuity is at x equals 2. So we'll go to x equals 2. And based on what we're seeing, we have at x equals 2, it looks like a jump discontinuity. So we have another jump discontinuity at the value x equals 2. Now, the next question is, what is f of 2? In other words, is it defined there? If we look down below, we have a solid dot when x equals 2 at the y value of negative 2. So f of 2 itself would equal negative 2. Now that we have found the f of 2 value itself, let's evaluate the limits. So let's take the limit as x approaches 2 from the left of this function. So if you approach 2 from the left, you'll get closer and closer to that y value of 2. So the left-handed limit at x equals 2 is 2. Now what about the right-handed limit as x approaches 2? If we approach 2 from the right, you get closer and closer, and actually is defined there at the y value of negative 2. So the right-handed limit's negative 2, left-handed limit's positive 2. That means the general limit as x approaches 2 of this function does not exist, since the left-handed limits and right-handed limits don't match. Now, one more thing we have to answer: is this function continuous from the left or the right? Well, definitely not the left, because it's undefined at that y value of 2, but it is continuous from the right because you have that y value of negative 2. So this function is continuous to the right in this case. So it'll have right continuity this time, since it's defined for the right branch. So that's everything about the discontinuity at x equals 2. we have a few more discontinuities. So let's go into the next one. Now, if we go to x equals 4, it looks like we have another discontinuity. And you see the shape of the graph at x equals 4, it never actually crosses x equals 4, but it bends around it going up infinitely. That means then that we have an infinite discontinuity at x equals 4. So infinite discontinuity is going to be located at x equals positive 4. Now, first question we have to answer is the function defined at this value, f of 4? Well, infinite discontinuities, again, are caused by vertical asymptotes, meaning the function's not defined there. So, in this case, f of 4 does not exist. But what we can do is take the limits. Let's start with the left-handed limit as x approaches 4 of this function. If we approach 4 from the left, you just keep going up and up and up until you get infinitely close to 4 and you go towards infinity, because this graph keeps going up and up and up. Now let's approach 4 from the right. So let's take the limit as x approaches 4 from the right of this function. Again, trace along the curve until you get infinitely close to x equals 4 from the right. It just keeps going up and up and up. You would also have a right-handed limit of positive infinity. In this case, we can say the general limit as x equals 4 exists. As x approaches 4 of this function, the general limit does exist. It's going to be positive infinity. Now the next thing is this function continuous from the left, right, or neither? Well, in order for the function to even have a chance of being continuous, the value of the function itself has to be defined at that particular value of x. As we've seen, for example, with x equals negative 4 or x equals positive 2, we did have a continuity from the right, but we don't have any value where it's defined for x equals positive 4. There's no y value you can define it as, so it's continuous neither left nor right. So this function at the point x equals positive 4 is continuous neither left nor right. So that's everything about the discontinuity at x equals 4. Now we still need to deal with a couple more discontinuities. Okay. If we look at x equals 6, it looks like we have another discontinuity. Looks like a jump discontinuity at x equals 6. So we got a jump discontinuity located at x equals 6. First thing again, let's try to define the function at f equals 6. Well, we have the left branch as for the limit as x approaches 6 and the right branch for the limit as x approaches 6. At both the left and right side, notice the y values aren't defined, but in between you do have a solid dot at y equals 1 when x equals 6. So f of 6 itself would be that y value of 1 where that solid dot is. Now of course we need to take the left and right-handed limits. So the limit as x approaches 6 from the left of this function, trace along your graph from the left as you approach x equals 6, you'll get to a y value of negative 3. So the left-handed limit at x equals 6 is negative 3. Now what about the right-handed limit as x approaches 6 of this function? you trace along your graph from the right towards x equals -6, you'll get to a y value of 3, or I should say get infinitely close to it. Now you see the left-handed limit does not match the right-handed limit. That means in this case the general limit as x approaches 6 of this function does not exist. And then the last question we need to answer is it continuous from the left or right? Well, at both the left branch and the right branch, the value of the function itself at x equals 6 is undefined, so it's continuous on either end. So at x equals 6, the function is continuous at neither the left nor the right. So that's everything about x equals 6. There's still one more discontinuity we can deal with for this graph. There is one more. If you look at x equals +8, you have another discontinuity, and it stops at x equals 8. It doesn't continue right anymore. You have an open dot at the y value of 2 when x equals 8, but that's an endpoint discontinuity. Sometimes you'll have undefined values at the endpoints even. That does sometimes happen. But you have an endpoint discontinuity located at x equals 8. So first thing again, now that we've identified what type of discontinuity it is, where it's located, is the function defined at x equals 8? Well, all we have at x equals 8 is that open circle at that y value of 2, meaning it's not defined there. So in this case, f of 8 does not exist. We cannot define the function at f of 8, so that doesn't exist. But we can still take limits. What about the left-handed limit as x approaches 8 of this function? Well, as we trace the curve from the left until we reach x equals 8, we'll get infinitely close to that y value of 2. So the left-handed limit's 2, but what about the right-handed limit as x approaches 8 of this function? Well, notice it stops being defined at x equals 8. There's definitely nothing greater than 8, so that means the right-handed limit does not exist. And based on the fact alone that the right-handed limit doesn't exist, that means the general limit as x approaches 8 of this function does not exist. And then, of course, we have to determine, is it continuous from the left or the right? It's definitely not continuous from the right because you have nothing greater than x equals 8. It's not even continuous from the left because, again, in order for it to have any continuity at all, the function would actually have to be defined at that value on the curve. And it's not defined there at that y value of 2. So this is continuous on neither the left nor the right at x equals 8. So there's everything about x equals 8. Now, that's going to be it for this lesson. Really, all you have to do, look at your graph, look for the discontinuities, be familiar with removable, jump, infinite, and endpoint. Know if you can define the function at that point. In other words, does it have a solid dot at a certain y value at that value of x? If it doesn't, then it's not defined. This should also tell you that sometimes the value of the function itself at that point is neither your left nor your right-handed limit. You have to look for that. You have to look for that solid dot. That's the value of the function. Sometimes it'll be one of your limits, but sometimes it's neither of them. So keep that in mind. Look for that open dot. That'll help you define the value of the function itself. And then, of course, take left and right-handed limits. And then, again, if the left-handed limit does not match the right-handed limit, the general limit doesn't exist. If those two limits exist and they match each other, then that's your general limit. And then, of course, the continuity part, where is it continuous from? In order to have continuity, either from the left or the right, especially let's look at a jump discontinuity. One of those two, like at x equals 2, is continuous from the right because the y value is defined there on the right, because you have the solid dot, so that would mean it's continuous from the right. So, removable discontinuities, it's always continuous neither. It's not continuous from either the left nor the right. And then, infinite discontinuities, it's not continuous either left nor right. So, and then keep in mind, you can have endpoint discontinuities where it's not even defined at the endpoint. And if that's the case, it's not defined either left nor right. If it is defined there, now had this been defined at x equals 8, of course we would have got a y value of 2, and we could have said it's continuous from the left, but that wasn't the case. So just keep all these in mind as you're doing these type of problems, looking at graphs like this and identifying discontinuities and finding function values, taking their limits, and determining whether it's continuous from the left, right, or neither. Now, next lesson I think is going to be a lot easier. We're finally done with continuity and discontinuity. We're going to do the limit of compositions of functions. So I hope everybody has a great day. Take care.